Physical science time. Work. So write that down, please. We're talking about work. One of your objectives says, explain the meaning of work. So, first of all, you've heard the word work your entire life. When we're talking in our daily usage, what does work mean? Raise your hand, please. I don't want to hear you all at once. Wait, what does work mean?
Like a job.
Okay, like a job. Okay, in your estimation, is that probably exactly what it means in the science definition?
No.
The fact that I even asked that question tells you no. So work must have a specific scientific definition. And what might that be? Raise your hand if you think you know. In your own words. Jacob?
Activity.
Okay, that's closer. Wait again.
The amount of force to make something move.
Okay, let's start with that. Force, and activity is not wrong, but we're going to get more specific. Force causing an object to move. And we would never normally specify this when we're talking about an object moving. I'm going to switch to picture-in-picture so people can see the board better. Force causing an object to move. Anytime we move, we're moving over a distance, right? So I would never normally specify that. Like I would never say, let's move this table over a distance. I would just say, let's move the table, right? But just because of the way the equation is going to work out, we're going to specify that force causing an object to move over a distance. In fact, we can say that work is force acting over a distance. Okay, and there's kind of a hidden implication in here that's extremely important for work. First of all, what two factors does work probably depend on? Since we've said it twice now. Distance and force. So somewhere we're going to have force, somewhere we're going to have distance, and we're of course talking about work. So think about our equation. If we're calculating work, how should we set up this equation initially? Probably work equals, right? Work equals.
Force times distance.
We know it's going to be force times distance. But let's talk about, it's actually supposed to be this, force cross distance. And cross product is something we're going to get to. We've talked about it once before. Do you remember in what case we talked about cross product before? We didn't actually talk about what cross product means, but I told you it has to be something cross something else as opposed to just times by. You remember what it was?
Momentum.
It was momentum. And momentum we said was mass cross velocity. In the same way work is force. And this cross product means something specific, but what it meant for momentum and what it means for this is that the force, God bless you, the force and the distance must act in the same direction. Force and distance, we're going to specify this a little bit more, but must, for now, for our class, must act in the same direction. So direction is extremely important for this. The distance something has traveled because of the work done to it has to match the direction the force was applying. This cross product very basically means that we only use the x component of whatever one of the force that we're talking about. It ends up being the force times the cosine of the angle. Have you ever heard of sine, cosine, and tangent, maybe? You know what any of those things are? No. Okay, when you get to trigonometry, hopefully, when you get to geometry or trigonometry, Mr. Snelly will start talking about those, and you'll say, oh, Mr. Kime already told me about those. And you'll say, oh yeah, what do you know about them? You'll say, basically nothing still, but at least I know their words, right? So this ends up being, we have to do some somewhat fancy mathematical operation to determine what this does to this, unless they act in the same direction. And if they act in the same direction, we just multiply. So, for you, these two things must be in the same direction. So, unlike our other equations we've done all year, we first have to ask ourselves, the first step, the new first step, is, are they acting in the same direction? And if the answer to that is no, you just give up right then and you say this. If they are not acting in the same direction, we write this. No work done. This is like a softer version of when you write on your math problem something like, what do you write? What is it?
No solution.
Yeah, no solution. No solution. A null set, right? Or it's kind of like in a race if it's D and F, did not finish, right? It's just like it's a separate category besides an answer. No work done. So once again, if we do a work problem, or if we're given a work problem, and the force and the distance are not in the same direction, we write no work done. The example here, I guess I'll use my teacup for this example. It's also, there's an example of a lady in your book, if you open with me to lesson 1. But there's a lady on 2 pages in our book, right? Do you see the lady? The lady is doing what in the first image?
Lifting.
She's lifting, just like I'm going to lift my teacup. Lift. What direction did I apply force in that example? Up. I applied a force up on my teacup, and which way did the cup move?
Upward.
Upward. Now, as I stand here, what direction am I applying a force to the teacup?
Nowhere.
No, I am still applying force, because if I wasn't applying force, what would happen?
You're-
It would fall. So I must be applying force still upward, right? So here's teacup. Can you see this on the screen? Ah!
That's a downward force, Mr. Kine.
Okay, here's my teacup. You had a question. What's the downward force? So here's the teacup. What's the downward force? Gravity. The force of gravity. What do we also call F sub g?
You.
No, you're thinking of potential energy. This is also the object's what? Almost. What's the force of gravity acting on an object called? Weight. It's weight. So F sub g, which is also
Mass.
W. Nope, not mass. Weight, which is different. And then what upward force am I applying?
Your hand.
The normal force, F sub n. If I hold it like this, it's better. Now, in the second image of the lady, and also me, what direction again am I applying the force? Up. Now I'm walking. Which way is the distance I'm traveling? Yeah, right now to you it's left, right? It's east. So if I'm applying a force up, and the object is moving east, am I doing work?
Yes.
Try again. No work done. Remember, they have to be in the same direction. Up and east are not the same direction. So we would write no work done. So when I lifted it, was work done? Yes. When I'm walking with it, is work done? No.
So
Yes.
if you,
So then why is it like if you were to carry a heavy backpack while you're walking, it's harder to walk?
So well, first of all, you're applying here. Here's you. Give me the pink real quick so I can dry your hair.
That's right.
Good enough. Okay, there's you, Wade. There's your arm. If you're hauling your backpack, right? What direction are you applying the force if you're dragging it? You're applying the force forward. Which way are you moving?
Forward.
Forward. So are you doing work?
yes.
Yeah. However, if you're lifting your backpack on your back, are you doing work? Nope. So, and you have to separate in your mind the like layman's definition of work, which is just like, I'm doing work, right? I'm gonna go hoe the garden or lift a sheep or work out, right? Those things mean work to us normally, but scientific work is a completely different thing, and it only happens if the force and the distance are in the same direction. I'm gonna erase some of this. I'm gonna put my teacup down. So what's our new first step? Hold on a second, Allie. What's our new first step?
See if they're the same.
Yeah, we have to ask ourselves, are those things acting in the same direction? Yes, Allie.
Is work measured in joules?
We're going to get there in 1 second. So our equation again was W equals F cross, do I have a capital D? Yeah. It's supposed to be lowercase. Pretend it was lowercase all along. Pretend it was lowercase all along. So, as we always do with our equations, we have W equals F cross D. Pretend it was lowercase. I made a mistake. What's the W? W is, we already talked about it, work. Measured in, we're going to talk about that in 1 second. F is measured in newtons. And D is distance. What do we always measure distance in the SI? Well, right now we measure in meters. So, just by this, what's our unit for force or for work going to be? Mathematically. Newton times meter. Now we're going to talk about it a little bit more. So go back in your notes real quick and tell me what SI base units was a Newton equal to? Okay. Kilogram times meter divided by second squared. We're going to multiply that again by what? Meter. Do you see how I've just taken this Newton and replaced it with what it's equal to in other units? It's just a substitution. Multiply again by meters. What's our new unit? Kilogram times meters squared divided by seconds squared. Do we already have a name for this? Look in your notes somewhere else. What's the name for this? So that equals a joule. I'll tell you, a lot of times it's not unconventional. In fact, usually we measure, when we talk about work, this applies especially to something called torque, which is a rotational force. We do measure torque usually in the SI in Newton meters to differentiate. But we usually measure work and energy in joules. Torque, which is, like I said, a separate thing that we won't talk about right this second. You might have heard of torque before. You might have heard of like a Torx wrench or a Torx screw. But yeah, it's basically a spinning force. That we almost always measure in Newton meters. The units come out the same. But these two, work and energy, we usually measure in joules to differentiate. So joules are usually how we measure work. Let's do a problem real quick before we end. So let's do two problems actually. Let's say Wade, remember him? Let's say he's applying a force of 900 newtons. He's got a heavy dang backpack to drag his backpack along the ground, okay? 900 newtons, and he moves it over a distance. How long do you think this hall is out here?
Probably like
Let's say it's 100 meters. Good. So let's calculate the work. So first of all, what's the first step?
Right the equation. Hey, it's not me.
Say it again, Mitchell.
See if they're the same direction.
See if they're in the same direction, okay? And are they? In this case. Well, I've already drawn on my diagram, we've already talked about, so yes, they are in the same direction. So what do we do next? What's our usual first step, but now it's our second step?
Right.
What is the equation?
W equals force across D.
Good. Okay, now what's the next step? Substitute, tell me what to write. Allie, tell me what to write.
So W equals, and then 90 newtons.
900 newtons.
900, oh,
Got a super heavy backpack.
Oopsies, I forgot that, sorry. And times 100 meters.
Good. Work in this case equals, this is a pretty easy problem,
9,000
9,000 what?
newtons, no, joules.
Joules. A lot of energy or a little energy? It depends, it's all relative, but this is, for hauling a backpack down a hall, that's really quite a lot of energy. Okay, now let's just do another, let's just do another simple example. If I dropped some eggs at the grocery store, I was going to pick them up and then haul them to the front of the store to yell at someone. Would I be doing work?
Nope.
No, so that's the other kind of problem you'll get. So remember, the point is, remember to ask yourself, is work being done, yes or no, before you actually do the math. Bye.